We have covered many different techniques so far for detecting water. Most of this involved kind of computing an index and doing some thresholding. We did the zero thresholding, we did the automated Otsu thresholding. Let's learn some more machine learning based techniques. Why we should use machine learning for remote sensing data? Because most of the problems in remote sensing require you want to know what the pixel represents. I can see something. What is it? Is it water? Is it crop? Or is it a car? Or is it a building? Right. So when you want to detect an object, that's a problem that is very suited for doing machine learning. Also, the data is noisy. If you had a pure observation, you can go to the ground and say, I can measure the reflectance, and I know that this plant has this signature, or this water in this reservoir has this signature in different bands. I can go and find those in my images and I can detect that. But since you have the whole atmosphere between the ground and the satellite, plus the satellite has some noise, you will not get exact match. So you'll see similar patterns, but you'll not get an exact match of those values. And this kind of problems are again very well suited for machine learning, where you just have data and the algorithms will figure out the pattern and try to match that. So instead of defining the rules yourself, you can use the data to figure out the rules in your algorithm. So one of the key differences between classical programming and machine learning is in classical programming, you code the rules in your program. So you'll say, I will take this data, I will figure out, I know what the rules are, and I will classify this data. In machine learning, you said, I have the data, I don't know what are the rules, but I have some data that tells you what is the relationship. You go and figure out the rules. Okay? So one starts with the rules, with the explicit thresholds and rules. Other starts with data. Right? So two different approaches to solve the same problem. So two different classes of machine learning. One is unsupervised learning. That means you just need the source data. You don't need to label any data. And you just give the source data and the algorithms do its thing and finds the pattern in the data. So these are also known as clustering algorithms. They are used to group things into different things that are similar. So another example would be you send some photos to the algorithm, it'll group into two piles, cats and dogs. It won't know which is cat, which is dogs, but it'll separate them into piles of photos of similar kinds. So similarly here, it'll divide your data into different clusters that are similar. You won't know which is which, but you can separate them out and then you can apply your own knowledge or some rules to separate them and label them. Supervised learning is the opposite, where you have some label data. You know some ground truth where you say, I know that this pixel is this value, or this pile is dogs and this pile is cats. You learn from that and figure out the rules that separate cats versus dogs. And then you can use that, apply the rules on other data, which is not labeled, and do that. We're going to focus this whole module on supervised learning because that's the more widely used algorithm. But I want to show one script on unsupervised learning, which is my favorite script so far for detecting water reliably. And again, by using some clever techniques, we can make this technique completely automated. So let's see how we can use an unsupervised technique for detecting water. Another note on kind of supervised versus expert system. In expert system, you are defining the rules. In supervised learning, you are giving the data, the system is defining the rules. Okay? So one point I want to highlight for everybody is that one is not better than the other. It's just different approaches to solve the problem. Do not think that because you use machine learning, you'll get better data, better results. It's just a different approach to the problem. Machine learning requires a lot of label data, very high quality label data. So you need to invest time in curating and collecting this data. Expert system requires a high degree of domain knowledge and a lot of understanding of the data to be able to code those rules. Both have their pros and cons. And again, when we are talking about water, so far, the best global data set for water is an expert system. Right? Even the machine learning approaches cannot match the quality of that data set at a global scale. So again, both have the pros and cons. We're going to focus on supervised learning in this module, but both have the merits. So explore both when you are encountering a new problem. We're going to explore these algorithms. We're going to do k-means clustering for unsupervised. For supervised, we're going to learn SVM and decision trees. I'm going to just show a demo of neural network. We're not going to cover that in detail. So let's say we want to detect water in a satellite image, and we want to use an unsupervised technique. So we have our data, which is the satellite image. How can we detect water pixels? Let's see a simple example. We're going to take just the two bands which are very different in terms of water reflectance than other bands, and two bands because it's easier to show on a 2D graph. So it's easier to understand. In practice, you can have as many bands as possible. So right now, let's just focus on these two bands. We'll take our image, we'll take 100 points across our image, 50, we don't know what they are, but we'll just measure the reflectances. So we'll say the green value for pixel 1 is 0.09, NR is 0.02, and so on. We have those 100 values, and that's our data. That forms our data for our unsupervised clustering. We take this data and we can give it to this algorithm called k-means clustering. This clustering will say, I will divide this data into clusters where the points are similar to each other. So here it'll take this 100 points and say, oh, the value 1 and value 5 are very similar to each other. I'll put them in the same bin. So it's going to divide this data into a number of bins which are similar, and it's an iterative algorithm. It'll try first initialize with the random clusters and then slowly improve on that by iterating and converge on clusters where the center of the cluster is closest to each point. So if you think about each point, it's assigned to the cluster where the center of the cluster is closest to it. So we'll take this data, and if you plot this data, this is what our data looks like. So these are all the different points that is sampled from our image, 100 points. If you give it to k-means clustering, you might get clusters like this. K-means will come and say, I figured there are 3 clusters in the data. And again, you did not have to do anything except just give the data. We just took 100 pixels from our image and we gave it to the algorithm. The algorithm did its thing and came out with these 3 clusters. And now you will be able to see all the different clusters assigned to each of those values. So that's the end of the unsupervised part. This is what unsupervised algorithm does. If you give some data, you'll get clusters. In Earth Engine, if you give an image and you say, cluster this, you'll say each pixel will be value 1, 2, 3, 4, whatever is the cluster number. And all the clusters at the same number will be colored the same way. So that's it. That's the end of the algorithm. Now, normally when you are doing unsupervised clustering, a human has to look at each cluster and say, what is cluster 1? I'll do some interpretation and say, oh, this looks like crops. So I'll note down, say cluster 1 equals crops. Cluster 2 is urban. Cluster 3 is water, and so on. But in case of water, we can do something a little smarter. So we can remove the human out of the equation. We can say, let's compute the NDWI of each cluster. So we take all the points that fall in each cluster and compute the average NDWI for each of those. Now, if you look at these 3 clusters, can you see which cluster is water? Water has high NDWI. So the cluster having the highest NDWI will be water. So now you can combine unsupervised clustering with a rule, a human-based expert system-based rule, and say, I will now select the cluster having the highest NDWI, and I'll label them as water. All the other stuff is not water. And now I've suddenly found water without any human input. So this is a really nice technique, which is quite robust. One of the key things about machine learning is, regardless of the distribution of how the cluster is, this cluster could be appearing very different in different parts of the world because the water might have different reflectances. But it's still robust to saying that, okay, all the water pixels look similar. I'm going to group them together and then find that cluster on that. And it's also very clean because you get very clean cluster boundaries here. Let's learn the kind of other approach to machine learning, which is the supervised classification. So again, classification is the process of turning your pixel reflectances into classes, determining what does the pixel represent. So we'll try to take an image like this. So we'll create a Sentinel-2 composite for whatever city that you want to create. And the goal for today is we'll do a supervised classification of the city and turn this into an image like this, where we'll determine that each pixel belongs to one of these 4 classes, either is built up, bare earth, water, or vegetation. And once we classify this, we can always select the water pixel and extract the water. So this is yet another approach. If you want to detect water, you want to do it in a way, you don't want to use any other data set that doesn't meet your needs, or you have your own data set. You can bring some training data and classify this. We'll learn the whole process, how this process works. We'll also be collecting training data for your city today in the class. Now, why classification? Well, this image is great, but it can only be interpreted visually. So somebody has to sit and say, oh, this one is water, this one is an airport, and so on. If you want to do anything automated, if you want to quantify it, say how much water, or how much water changed between 2 dates, or when did a new airport come up, things like that, right? So you don't want to go and look at each pixel of the image. You can apply an algorithm to classify the image into whatever it represents. For change detection, again, it's easier to compare class to class versus just raw reflectance values. In supervised classification, we start with the same process. We take our image bands that we have, we sample them, and we get the reflectance values. But there's an additional step to the supervised process, that whatever pixels we have sampled from our image, we sit and label them. We say, I look at this pixel, and this pixel is this class. In this example, we are doing a simple 2-class detection, water versus not water. So we'll go and label each pixel that this pixel was water, this pixel was not water. And that means when we plot them, this is what the data looks like. So our data is that we have labeled them. The blue ones are water, the gray ones are not water. And if you plot the reflectances, this is what they look like. Now, we want an algorithm to look at this data and come up with a method to say, given any pixel value, how do I separate them into water versus non-water? So this is the data. These are our labels. How do we build a model of the data? And there are kind of 3 approaches that we'll cover. One is a simple approach, the older machine learning methods. Second, we'll cover the decision trees, which are currently the most popular machine learning methods, and then a neural network, which are more advanced deep learning methods. So SVM was a kind of an older machine learning algorithm. It's a kind of simpler algorithm where it's ideal for a 2-class classification. You take the data and you say, this is my label data. SVM will run, look at the data, and separate them into 2 classes by dividing them through a plane. So if it's just a two-dimensional data, it'll come up with a line and say, anything above this line is water, anything below this line is not water. If it's a 3-dimensional data, you have 3 variables. You can think of like all the points in 3 dimension. It'll come up with a plane and saying anything above the surface is water, anything below the surface is not water. So the job of the algorithm is to find that plane that separates those 2 classes. So if we give this data to SVM, the result of the SVM algorithm would be a line like this. So that's your model. It says, in this data set, I discovered this pattern that anything above this line is not water, anything below this line is water. And now you can say, go and classify every other pixel. We only labeled maybe 100 pixels. How do we know what other pixels are? So it goes through each pixel of the image and it says, oh, I found a new pixel and the pixel value is here. This is the green reflectance. This is the NIR reflectance. It'll ask the SVM algorithm, what is this? And say, oh, this one falls below the line, so it must be water. So you label this as water. You go to the next pixel and say, I have found a pixel. This is the value. This is the reflectance in NIR band. This is the reflectance in green band. What is it? And it'll say, okay, this is above the line. This is not water. And that's how it goes and classifies every pixel. So you start with the small sample data, build a model, and then apply the model on rest of the data to classify the image. SVM was quite popular, maybe I think in 80s and 90s, till the decision tree algorithm came up. So decision trees is good for multi-class problems, and in remote sensing, most of our problems are multi-class. Even when you are working on problems like water versus non-water, it is easier and more accurate to do a multi-class classification and select water versus just do water versus non-water. It's much simpler for model to understand, saying there are actually 7 classes here. I'll detect all 7 classes and select water, versus saying there are 7 classes, I'll select water and then figure out what rest of it is. So even for simple multi-class problem, 2-class problems, a multi-class approach is more preferable for remote sensing problems. Also, this is more understandable. You can see it builds a visual tree or a flowchart-like structure where you can interpret the algorithm much more easily. It's currently the most popular machine learning algorithm for remote sensing. If you read any paper published in the last 5 years, or anybody's using any kind of classification in Earth Engine or outside Earth Engine, everybody agrees that this decision trees perform much better than all the other counterparts. And there are variants of decision trees, but again, this class of algorithms generally perform much better than other things. It's also very popular because it can be used for both regressions and classifications. So classification is a process of assigning a single class. Given set of pixel values, you say, this is class 1 or this is class 2. It can only predict numeric integer values. Regression can predict continuous values. So you can use the same algorithm and say, I have these values, predict the amount of rainfall, predict the amount of harvest, right? And you can use it for regression as well. So let's see how decision tree would take this data and work on it. So same data set, we gave the same 100 points. Some points, all points are labeled, water versus non-water. The decision tree will look at this data, do its thing, and it'll generate a tree that looks like this. It'll generate a flowchart that says, oh, look at the green reflectors. If it's below X, it's less than X, do something. If it's greater than X, do something else. If it's greater than X, check the NIR reflectors. If it's greater than Y, do something. If it's less than Y, do something. And this is what it is. So it says, if your input, look at your input pixel. If green is less than X, it's not water. If it's green is greater than X and NIR is less than Y, it's water. And so on, right? So we now have a flowchart that allows us to make a decision. The most important concept to understand here is that X and Y, the thresholds, were determined automatically based on the data that you gave to the algorithm. You don't have to say what is X and what is Y. You just have to give the label data. The decision tree will figure out what is an appropriate value of the X and Y here. Okay, so if you are building an expert system, you'll also do something similar, but you'll have to go and figure out, okay, NDVI greater than 0.5 is this, NDVI less than 0 is water, and so on. Here you just say, I have some data, I have labeled them water versus non-water. Out comes this flowchart. Okay. And now when you have a new pixel, so you say, I have a model, now go and classify an image. It starts looking at each pixel of the image, and it says, I have one pixel here. And it says, okay, let's do a flowchart. Is green less than X? We say, no, green is greater than X. Then it comes here. It says, is NIR less than Y or greater than Y? And we say it's greater than Y. Then it says, we'll label this as not water. Right? And it does the same process for every pixel, and it classifies that. So the advantage of this is once you build this model, you can see it. It's easy to understand. If something got misclassified, you can look at the flowchart and say, this is why it happened. One problem with kind of decision trees is rarely your data is this clean. Right? Real world data is not this clean. What if you had data that looked like this? Maybe there was a water pixel right here. And one of the kind of hallmarks of Earth observation data is it's noisy. Right? There'll be noise like this. So you want your model to learn this pattern, right? That you want your output to look like this. But what will happen is if you run a decision tree on this, it'll say, oh, there's a water here. So it'll try to say one more thing. If NIR is greater than Y, one more branch. Check if green is greater than Z. If it's greater than Z, check if its NIR is greater than W. If it's less than W and less than Y, then it's water. Like we'll build one more tree. We'll try to build a model that exactly reproduces your input data. And that means in your real data, if there was a pixel here, it'll say, oh, this is water. This is water. It has learned from the mistakes in your training data. And this is called overfitting in machine learning, where you have noise in your data and your model doesn't learn the pattern. It just tries to mimic the data in a very close way. So you don't want that. Right? You want your model to actually learn the patterns and not really reproduce your training data completely. That's where this algorithm comes in. So decision trees were powerful, but they had this overfitting problem. So what the solution that machine learning engineers came up with is that let's not use only one tree. One tree will overfit to the data. Let's use multiple decision trees. So let's say we have 1,000 points of our training data set. We'll select 500 of them randomly out of this, build one tree. That tree might be overfitting to that 500 subset of 500 points. Then we'll take another 500 points randomly from the 1,000, build another tree. And we'll do this like, we'll build 50 different trees, each from a random subset of the data. Each tree might have overfit to that localized version of this data. But when you ask each tree, so when you're at a prediction time, you ask that I have a pixel, what is it? And you ask all 50 trees. 40 might say it's water, 10 might say it's not water. And you take the vote of the majority and assign that to this final class. And this results in a much better model that doesn't overfit and actually produces the pattern of the data much clearly. This kind of techniques are called ensemble learning. That is, you use not one model, but multiple models together, and you kind of combine them together to build a more larger, more accurate model. This is a visual of how a random forest works. You have multiple trees. Each tree predicts a class that, based on that, whatever it's trained on, and then you take the majority voting and assign the final class to it. This may seem counterintuitive, but in practice, it works quite well. And random forest doesn't overfit to the data like a single decision trees. It carries forward all the parts of the decision trees. It's explainable, it can do regressions, and it's easy to understand, and so on. So currently, random forest outperforms almost all other machine learning algorithms. And in Earth Engine, that would be my recommendation to try. If you're doing supervised classification, start with random forest. There are 10 other algorithms available in Earth Engine. It's just one line change. If you want to try SVM and say, I have this data, change one line, it'll run SVM. Change one line to run a simple decision tree and so on. But okay, all the studies that I've seen, all the projects I've worked on, random forest by far outperforms everything else. So it's a good first choice for you to try it out. Yeah, interesting question. How many trees should we use? What's an optimal number of trees? And as with everything else in machine learning, the answer is it depends on your data, and you have to try out different number of trees and pick the one that works best. So there is no mathematical theory that says, given this data distribution, you should use this tree. What you typically do in machine learning is you build a model and say, I will try 10 trees, 20 trees, 30 trees, 100 trees, and I'll pick the model that works the best. And it's typically part of your machine learning process. And it's all automated. We'll teach you this process where this is called hyperparameter tuning. One of the parameters for the model is how many trees. We don't know. So we'll try all different possible values, and we'll pick the one that performs best. And again, you ask any machine learning expert you meet and say, oh, you use this model. Why did you use this model with these parameters? And you say, oh, we tried everything and this one works the best, right? That's the kind of practice of machine learning, that you set up your workflow so that you try different things and you can pick the one that works the best. That's where Earth Engine kind of really comes in handy, because we have a lot of compute power. Because random forest requires a lot of compute power, even for like a single image classification. And you say, repeat this 100 times for different combinations, you definitely need that power to do different trial and errors.